application of all these wonderful quadratics, and actually there's way more applications of quadratics than I've ever begun to show you, but this particular one, yes, we're going to talk projectile motion. So what do I mean by projectiles? Objects doing what? Flying through the air. Okay. Why don't objects just fly through the air forever and stay up there? Because of lovely old gravity. Well, in our case, with our algebra right now, we can only shoot our objects straight up and down in the air. So we're going to shoot something up. It's going to go up to a certain height. Then what's going to happen? It's going to turn around, and it's actually going to come straight back down where it was before. So we're doing projectile straight up and down motion. If we actually want to shoot them off at an angle, like the basketball player graph you did, or shooting a missile, something like that, to shoot them off at an angle, we have to put a trig function into the equation, which gets a little trigonometry involved. So if you would love to do that, then you need to take pre-calc, because then we shoot them off at angles, and we can figure out how to hit the basketball hoop or put a golf ball in the hole. So we're going straight up and down right now. What I don't think a lot of people realize about projectile motion is that it mirrors itself. When you shoot something up in the air, after the first second, it will have reached a certain height, after 1 second. After the next second, will it go as far? Say I have it going up at 75 feet per second. Will it go as far as the second as it does in the first one? Why do you say no? Because gravity's doing what to it? Gravity's going to slow it down. So it won't travel as far. The second, it won't get as far as the first time. And as we keep going up on second 3, it's going to slow down some more. It's not going to get as far. In second 4, it's going to get even smaller. Say in second 5, it reaches the top. What happens for a moment at the top, at that exact moment you're on the top? What does it have to do? It goes up, it hits the top, it has to stop. For a split second, it stops. It freezes in the air, and then what happens? Gravity pulls it back down. And this is the cool part. When it comes back down, it stops, so it's going really slow. So gravity starts to pull on it, but it's not going to get it going very fast yet. So when it comes back down, it comes back down in the exact same increments. The first second, it won't come down much. The second section, it'll gain a little more. The third section, now we're picking up speed. The fourth second, okay, we're really going. It mirrors itself. The number of seconds it takes it to go up is the same number of seconds it takes it to come down. And a lot of people don't want to believe that one. But gravity's pulling on you with a constant amount of force. It's going to happen every time. It mirrors itself. So if you shoot a projectile in the air and it takes it 6 seconds to get to the maximum height, how many seconds is it going to take it to get back down? 6 if it gets to the same height. Same way, if you start a projectile, you're standing on top of a building that's 20 foot tall, and you shoot something upward, how much time will it take it to get back down to the 20-foot level? It'll be exactly the same. It's mirrored every time. So the question is, how on earth do you do this, and what does it have to do with quadratics? For right now, you all have to trust me that this formula exists. We actually create this formula in calculus, but for right now, you have to trust that this formula is accurate. But I think I need to do a quick reminder. Back a couple chapters, back in September, I had you do something like f of x equals 3x squared plus 4. And I said find f of 1. What did that mean you were supposed to do? Put 1 in for x, okay? And that would give us 7. Did you actually do anything with the f of 1? No. Okay. We're doing the same thing, but instead of having f of x, we're going to have h of t, where h is the height it is at any moment, and t is the amount of time it took. So it's the same thing as f of x. You don't do anything with it. It's just a notation to say, hey, this is the equation for height at any time t. The equation looks like this. Kind of nasty. My students usually remember it as h of t equals half at squared plus bot plus so. Do you see where they're getting those? Half at squared plus bot plus so. If it works, it works for you. If it doesn't, sorry. But that particular equation will describe the motion of anything going up. If I put t in for 2, that means I'm asking it how high will it be after 2 seconds. If I put 5 in for t, it'll tell me how high it is after 5 seconds. This equation gives you the height of the projectile at every moment in time. So the question is, what on earth do all those symbols mean? What do you guess h is? H is indeed height. Okay, t is probably, yes, time. Alrighty, the biggie, what's a? We're moving, we're doing motion. A. What do you get in trouble for if you get in your car and do this in the parking lot? If you accelerate too fast? A is acceleration. Now, this one's kind of important. It is the acceleration of gravity. How fast is gravity pulling on you? As long as you are here on Earth, though, we know exactly how hard gravity is pulling on us. Gravity is known. So if you are here on Earth, A is going to be one of two numbers. If you are working with feet per second squared, acceleration is going to be negative 32. We just know that number. That's what it is on Earth. Okay. The other one is if you're working in the metric system with meters. Anybody know that one? It's negative 9.8. So those two numbers, you're going to fill one of those two in every problem. You're going to have to look at the problem and go, am I in feet or am I in meters? If I'm in feet, I'm going to use negative 32. If my problem is in meters, I'm going to use negative 9.8. But those are known about gravity. Now, if you go off to the moon, those change because gravity changes. Okay. So T, again, once again, is still time. That doesn't change. Now, I got asked last chapter, what are the little O's? Why is there O's on it? Those are zeros. Why would they write, well, I guess let me ask you this. What do you think V is? It's velocity. So why would it have a 0 on it? It's initial velocity. What does it mean to call it initial velocity? The beginning. What time are you at if you're at the beginning? How many seconds are you on if you're at the beginning? You're on 0. If you see a subscript, those are zeros, that means at time 0. So at the very start. So we do indeed. We call that initial velocity. And it's just how fast are you moving at the moment this starts. Okay. Okay. So, I don't know who picked it in math, but somebody picked it somewhere down the line. That's what's going to be position. I never have figured out any rhyme or reason for this, but S is position in math, okay? Math and science, we like S for position. Okay, but in this case, by position, I mean how far off the ground are you when you fire it? If it's sitting on the ground when you shoot this projectile up, then you have S would be 0. But if you're standing on top of a building and you throw something upward, then your position is going to be how high you are at the moment you throw it. So this is the initial position. Where is it at off the ground at the moment you start? So, okay, that's a good question. Velocity is, she asked me whether you're shooting it upwards, or say you were on top of a building, you throw it downwards. What do you do differently? Okay. If it's going upward, your velocity will be positive. If you're going downward, velocity will be negative. So you, depending on which direction you're throwing, you change the velocity number. All right, so we're going to go devise our own problem here, solve this. And so we're going off. Mr. Hermrich has decided he needs to go out and see the world. And to do so, he's decided to join the circus. Okay? And, you know, he said, well, what jobs do people have for me? And they said, well, we have this nice device over here. Can you tell what it's supposed to be? Yeah, we need somebody to get shot out of the cannon. Our last guy had a bit of an accident, and, well, we need a new guy to get shot out of the cannon. So, person's going to, of course, be standing in the cannon here. Little platform, they're going to get launched out of the cannon. Okay? You all get to pick. How fast are we shooting Mr. Hermrich upward? How many feet per second would you like him to be moving when he comes out of the cannon? I got 100. Got a nice round figure. You all want 100 feet per second? Okay. So, he will be coming out of the cannon, moving at 100 feet per second. Okay. We're going to assume, since his feet here are, he's off the ground, so he's got to have an initial position. He's off the ground a little bit. So that initial position is going to be at 5 feet. That's how high his feet are off the ground. Okay. There are two kinds of questions I can ask with these projectile problems. I can ask you, how high will the object go? And I can ask you, how many seconds does it take before they hit the ground? So we're going to answer both of those here, I hope. Well, maybe not. So how high do we go? Before you can do any of these, you have to start out and have the equation. So we need the equation first thing. So I need you guys looking at your notes. What acceleration of gravity are we using in this problem? Are we in feet or meters? We're in feet. So his acceleration would be negative 32. Okay. T is your variable. It's like your x in your quadratic equation. So we're going to have t squared. What's the initial velocity? How fast is it moving when you shoot it? Or in this case, shoot him. 100 feet per second. So 100 times t. And your initial position? How high off the ground is it when you shoot it? Shoot him, 5 feet. Then we are going to, of course, clean that up. I'm going to take half times 32 and get negative 16. So there you have a nice quadratic equation, and that will give you his position at any time. So if I said put 1 in for t, if I said find h of 1, that would tell you how high he will be after 1 second. If I said find h of 10, that tells you how high off the ground he will be after 10 seconds. So you just put numbers in. But in our case, I want to know, what will his maximum height be? How high will he actually fly? And this is where you have to make a decision. Are we talking, his maximum height, are you solving the equation or are you finding the vertex? if you want maximum height. Vertex, yes. You see maximum? No, we can't talk. You want vertex?
Anyone that still needs to turn in an eligibility form, please do so today, immediately after school. Make sure you get it signed and brought to Mr. McLennan as soon as possible. Also, any students want to go to Emporia for the state volleyball tournament on Friday, please sign up. We need at least 10 more riders. So make sure you get into the office and sign up. Have a great evening.
So, if you're wanting the maximum height, you have to do x is equal to negative b over 2a. So, in this case, what's negative b over 2a? A negative 100 over 2 times negative 16. So we need to do 100 divided by 32, which is 3.125. They're going to round these off to 2 decimals, so you can go to 3.13. So what's that mean, 3.13? In our case, our problem isn't x. Our problem, x is actually t. So he's going to go upward for 3.13 seconds. Okay. Then I want to know how high is he going to get. So how will I get how high he's going to get? Bingo. You put it in there, and you ask yourself, oh, what do I get if I put 3.13 in there? Well, I'd have negative 16 times 3.13 squared plus 100 times 3.13 plus 5. And you would crunch the numbers. Anybody want to take a guess? How far high will he go? What do you think? 82 feet. Anybody else? 31. Oh no, he's going 161 feet in the air. Actually 161.2 to be more exact. Will he survive, or will we put a net under him? That's the question. The second question we'd like to be able to answer is, how long will it take, or actually let's rephrase that. How long does Mr. Hermrich have to think about hitting the ground before he does? This is the other side of our problem, and one you have to be aware of. The key thing is to ask yourself, what do I know about ground level? He went up, he comes back down. Since our formula only has height and time in it, do I know the height or do I know the time? Well, sure, I know the height. At ground level, I know the height is 0. So when you're solving a problem asking when it's going to strike the ground, you're setting the height equal to 0. So we would be taking our equation and setting it equal to 0. And we now have in a quadratic we need to solve for time. So now you have a choice. You can factor it. But I don't think this one's going to factor. You can do completing the square, graphing, or quadratic formula. My pick would be, of course, the quadratic formula. So if we put it into the formula, we know it would be negative b, which is negative 100, plus or minus the square root of b squared would be 100 squared, minus 4, a is negative 16, and c is 5. All over 2 times a, which would be negative 16. Now this is not going to be the greatest thing to work with, but you're going to simply want to plug this in your calculator and produce the result. Now you will have to do this as 2 separate problems. You'll have to put it once in with the plus and once in with the minus. When I put it in with the plus, I get a result of negative 0.05. When I put it in with the minus, I get a result rounded off, of 6.3. Now, which one would be the logical answer for the amount of time it's going to take? Well, we don't think he went backwards in time, so it must take 6.3 seconds to hit the ground. Or, we hope for Mr. Hermrich's sake, someone decides to pull out a landing pad, one of those great big cushions, or some type of a fireman's safety net. I'm sure he'll want to be shot out of a cannon again. So, until next time, enjoy. You're going to be practicing. You have 4 problems on your homework today that I already told you about. And then you'll be starting to work on a worksheet with partners. It has a mixture of the problems we've done in this chapter, the different application problems. You'll be working on it today, and then we will be finishing in class next time. And I want you to turn those sheets in to Mr. Hermrich at the end of the hour. I don't want you to keep them in case somebody's absent. I don't want your partner to be stranded. So have a great afternoon and work hard.